so I'm going to show you two calculations. One, just a general Dalton's law problem, and then I'll show you a problem with the Dalton's law of using it to calculate collecting gases over water. All right, so the first one here. What I have here is find the total pressure, so I know what I'm looking for. I'm looking for the total pressure here. So I must have a mixture of gases if I'm looking for a total pressure. I have a volume of 23.4 liters, and I have moles of nitrogen, which are equal to 2.65 moles of nitrogen, and my moles of, what's the other, oxygen, which is 1.75 moles. And all of this is at a temperature of 30 degrees Celsius. But if I had 273 here, I want to get rid of that and make it Kelvin right away. 303 Kelvin. So the idea is that I have a container, it has nitrogen and it has oxygen gases in it. Okay, so I've got a mixture of these two gases. Okay, the volume is the same, the temperature is the same. The only thing that's different is the moles of those two gases. So what I could do is I could say, okay, total pressure is equal to the partial pressure of nitrogen plus the partial pressure of oxygen. I got two options here. I could use this and calculate my partial pressure of the nitrogen, right? Plug in the moles of nitrogen, plug in R, plug in T, plug in V. I'd find my moles of nitrogen. I could solve for that. And I could do the same thing for the oxygen. Moles of oxygen, RT over V. And if I plug in for the oxygen moles, plug in the volume and the temperature, and plug in R, I'm going to get a partial pressure of oxygen. Then I add those two up, and I can get the total pressure. But there's a faster way. And the faster way is to know that the total pressure is equal to the mole total times RT over V. So what I can do is I can add up these two numbers of moles and say that the total number of moles here is actually equal to 4.40 moles. That's the mixture of gases. So if I treat these as just one gas, it doesn't matter if it's nitrogen and oxygen. You can have any gas combination you want. They act independent of each other. So what I can do now is I can say, okay, my total pressure is equal to 4.40 moles times R, which is 0.08206 atmosphere, liter, mole, Kelvin. I do this because I want to make sure everything is going to cross off properly, right? I want to make sure that I have Kelvin temperature, that I've used moles, and on the bottom, my unit is 23.4 liters. So the liters cancel. This is what I get a lot of students ask me, what's the unit for pressure? What's the unit for pressure? Well, if you're using R, it's going to tell you. So my final pressure, once I do all that calculating, comes out to 4.67 atm. So the total pressure in that container is 4.67 atmospheres because of the combination of the two gases. Now, if you want to do these two separately and then add them together, you're going to get the same results if you want to try that. All right, so you got carbon monoxide gas is being collected, 25 milliliter container using water displacement. So same idea, I'm collecting the carbon dioxide over water. Got water here, and so the idea is that I have carbon dioxide gas and I also have water vapor in here. So I have a mixture of gases. So I got to keep that in mind whenever it says using water displacement or collecting over water. Water displacement because I'm moving the water out of the way. All right, total pressure. Total pressure in that container is 6.078 kilopascal. The volume is 25.6 milliliters. And my temperature is equal to 22 degrees Celsius. I'm right away going to add 273 to that. And if I add 273, my temperature comes out to 295 Kelvin. Okay, so I've got my new temperature. What I want to do is find the moles of CO2. Okay, so I'm looking for moles of CO2. They also tell me that the partial pressure of the water is equal to 19.8 torr. All right, now notice the units here are different. What a pain in the butt. So because of the fact that here, I'll show you what we're going to have to do. So we're using PV equals nRT. Why PV equals nRT? Because I'm looking for moles. I'm not changing anything, no pressure, temperature changes, so moles are equal to pressure, volume over RT. So what I'm going to need to know is my pressure, my volume, my R constant, and temperature. Well, the pressure, what I need to know is just I don't want the total pressure, and I don't want the partial pressure of the water. I need the pressure of carbon dioxide. All right, so how do I get that partial pressure of carbon dioxide? Well, pressure total is equal to the pressure of carbon dioxide plus the pressure of the water. So my pressure of carbon dioxide has to be the total pressure subtracted from the water. So partial pressure of carbon dioxide. So I have to get these two in the same units. Now, I'm not going to do this just to save some time here. I'm already going to have these two numbers calculated. You would just do kilopascal to atmosphere. I'm going to convert them both to atmospheres because I want atmospheres in here because the R that I'm going to use is the 0.80206 atmosphere liters. It's the one I like to use, so I'm going to always convert to atmospheres. So when I do that, my total pressure comes out to be equal to, let's see, total pressure is 0.06 atm minus my partial pressure of the water, which is 0.0260 atm. Again, I made the conversion from torr to atmosphere, from kilopascal to atmosphere. My partial pressure of the carbon dioxide comes out to be equal to 0.0260 atm. Okay, there's my partial. Now that's the one that I want to plug into my equation. All right, so to go ahead and finish this, I'm just going to say the moles of carbon dioxide are equal to 0.0260 atm, my partial pressure of the carbon dioxide, times 0.08206 atmosphere, liter, mole, Kelvin, times my, all right, see what I did? Look, I already made a mistake, so I want to go ahead and fix that. Get rid of the R, because R doesn't belong there. My pressure should be times volume. Oops, going a little too far there. ATM, pressure times volume, 25. Now again, look at this, 25.6 milliliters. I got to get rid of that and convert that to liters because I'm using R has liters in it. So again, by using R, I can make those connections or corrections easily. So it's 6 liters. So let's go ahead and make this 0.0256 liters. All of that over R, which is 0.08206 atmosphere, liter, mole, Kelvin, and then I know that my temperature should be in Kelvin already, which I already did, and I said it's 295 Kelvin. Kelvin cancels, liters cancel, atmosphere cancels, leaves me with a unit of mole, and when I do that calculation, I end up with 32.2 moles of CO2. Okay, and there's your final answer. All right, we'll take a look at more problems in class, and I will see you later, guys.